Okay, so our speaker today is Federico Bambozzi, and his title, as you can see there, is Derived Non-commutative Geometry. Please, Federico, go ahead.
Okay, thanks for the invitation and giving me the opportunity of presenting my work in this seminar. And yeah, maybe a better title would have been Derived Non-commutative Algebraic Geometry. So yeah, geometry is a very broad topic, but today we will focus on algebraic geometry. So everything is in the algebraic setting. So the plan of the talk is the following. First, I will briefly recall some of the history of which motivates the problem I will try to discuss. That is, like, one of the main basic problem is the construction of a spectrum of a ring. So now I mean non-commutative. So a ring can be also non-commutative. And so this is a problem that has been discussed and attacked by many authors in the last decades. So it has a long history. And then I will introduce some ideas, some standard ideas from homological algebra and some geometry. Also will recall some of the basic of the theory of Grothendieck topologies. That is the main tool, one of the main tools we use. And then I will propose a definition of the Zariski topology in the category of the G algebras. So now the G algebras not necessarily commutative. And then I will comment on the resulting construction and show some example of also of non-commutative spectra of rings that are possible to compute. So so the style of this talk will be a bit informal because the techniques here are a bit involved. There is, if you want to really write everything precisely with the correct language, you should use infinity categorical language, and so recall a lot of notions. So I will be a bit sketchy and I mean informal. So I will say that things are possible, but not entering details on how things are done, and refer to literature for that. So let's
May
start.
I interrupt you one second? When you say the spectrum, you mean a topological space together with a sheaf of what? These algebras?
There is a full talk about that. So we'll see.
Okay. Okay.
It's both things, and you will see that there will be problems of several sorts coming up. So this story is motivated by the duality theorems that classically appear in geometry. And first, I want to say that this is a project that is a work in progress with several authors, and the result of this project will appear in several preprints that in the next years will appear, one of which should be almost finished. And so some of the main people that are working with me in this are Matteo Capoferri, Kobi Kremitzer, and Simone Murro. And but the point, our goal is to have some non-commutative version of the duality theorems that are nowadays classical. The most basic prototype is the Gelfand duality that says that there is a duality of categories between commutative C-star algebras and compact Hausdorff spaces. So duality means contravariant equivalence, contravariant equivalence of categories. So this means that the opposite category of C-star algebras is equivalent to the category of compact Hausdorff spaces. And there are a lot of such kind of theorems in literature, so that are at the basic of many theory of geometric spaces. For example, algebraic geometry is founded over the duality between affine schemes and commutative rings. And okay, in the Gelfand case, the duality is realized by the Gelfand transform. Here is realized by the construction of the spectrum of a commutative ring. And then there is a duality between smooth manifold and smooth algebras that are the Frechet algebras of smooth functions on smooth manifolds. And there is also the analytic version of this thing with Stein spaces and Stein algebras. Stein spaces are spaces that are determined by their function of analytic function over there. And the Stein algebras are precisely the algebras of analytic function on Stein spaces. And there is a similar story that you can make these dualities in the proper setting. Here, for example, you will have Frechet algebras with continuous homomorphism in the Stein case and in the smooth case, for example. But okay, and these are just few of the most important examples, and there are many, many more appearing in literature. And the common feature of all these kind of dualities is that they, on one side, start with some category of algebraic structures, usually some algebras with some maybe extra structure, and they associate to it a geometric, topological space, maybe with some extra structure like a structure sheet. And they realize then some duality between the opposite of this category of algebraic objects, so some algebras, with some category of structured topological spaces of some kind. But they always require the multiplication of the algebras to be commutative. And since the beginning of this appearance of this kind of dualities, people have asked what to do in the non-commutative case. So in this kind of construction, the first step is to define a topological space associated to these algebras that is called the spectrum, and then maybe to add the extra structure, like the structure sheaf. And so the first step is the construction of this spectrum functor. And for non-commutative algebras, since the beginning, it has been attempted to extend this approach, but not a lot of success has been obtained in this direction. And the goal of this aim toward non-commutative geometry is, for example, in the algebraic situation, is to have like a diagram of functors going from like rings. So rings is the category of all rings, maybe non-commutative, and then a non-commutative spectrum functor that extends the spectrum functor of algebraic geometry. And the vertical arrow is just the inclusion of commutative rings inside the not necessarily commutative rings, and to have that this diagram commutes so that this new non-commutative spectrum extends faithfully the classical construction, but also having the property that is reasonable, so that also it gives an empty spectrum, if and only if the ring on which I'm computing it is the zero ring. Otherwise, it's not a good functor. And people tried many constructions of this kind of functor. And at the end, recently, in 2012, Reyes proved that no such a functor exists. And even in the sister algebra case, so I mean, extending Gelfand spectrum to non-commutative sister algebras. So there's two versions of this theorem.
But wait a second. But so what you mean is that it doesn't exist that is functorial for all ring homomorphisms.
Yes, exactly. Yes, exactly. So if you look in literature,
because the Gelfand spectrum isn't.
Exactly.
The Gelfand spectrum isn't functorial either.
Yeah, exactly. I was going to explain precisely that in literature you find two kinds of construction. One that is functorial on the whole category of rings, but that will give some empty spectrum to some non-zero rings. Or you will find some construction that gives a spectrum that is non-empty for all rings, functoriality, you may need to restrict like your category to only some special class of morphisms between rings, or maybe some special class of rings, etc. So you can't get both. And in all examples, no one was able to have both properties. And then the explanation for that is that it's possible. So it's just not possible to get this construction such kind of functor. So I will not get that, but I would like to convince you that there is a construction that is natural enough and simple enough that it doesn't matter if it's not precisely the same as the construction of the spectrum of algebraic geometry. So yeah, for this kind of failed attempts, some people lost a bit of hope of getting the spectrum functor, and it tried to bypass this problem just working formally with the dual category of algebras or rings or whatever. But I will try to argue that there is still a bit of a hope of getting some meaningful construction, even in the non-commutative case. So for doing this, I will heavily use the concept of Grothendieck topology, and I hope that you are very familiar with this. I will give a briefly recall. If you are not very familiar with the notion of Grothendieck topology, you will have hard time today. And so Grothendieck topology on a category is a family of covers for any object. So fixing any object of the category, I have a family of covers that satisfy the Foley axioms. So if a family that consists of isomorphism is a cover. The covers are stable by pullbacks. So like if I take a cover and any morphism to the target, and I take the base change family, I get a cover. And if I compose two covers, so I get a cover from an object and I cover all objects, all the sources, domains of this cover with other covers, then I compose, I get a cover of the initial object. So this axiomatic somehow summarize how open subset behave in a topological space, and extend these properties to families of maps in any category. What we will try to do is that if we have C is a category that is like the opposite category of the G algebras or rings or whatever, and the topology is nice, we will restrict this a topology, a nice topology that we will define on this category, on the category over a fixed object, and we would like to get a set of maps from which we construct the spectrum. So what I want, how I present this better, I just work out the classical example, how you get the spectrum of algebraic geometry in this way. So the main example is the Zariski topology, and we want to mimic what is happening with the Zariski topology for commutative rings. So the Zariski topology can be characterized in a purely algebraic categorical terms using only terminology and concept from category theory. So I can characterize a morphism between two commutative rings that precisely correspond to an open embedding for the Zariski topology of the associated spectra by the property of being a flat epimorphism of finite presentation. So epimorphism, I mean epimorphism of rings. So I think I do not have to explain the meaning of these words, but if you are unsure about the meaning of anything, just ask. Okay, so these are basic property of maps between rings, and then this describes the family of open immersions. for the Zariski topology, and then I want to say when a finite family of these open embeddings cover the space without knowing that the space, what spec A is, because I want to reconstruct it from the topology on the category of schemes. I say that this, I mean, one can check that if a family of open embeddings cover and covers, I mean, it's subjective as a map of associated spectra, if and only if it satisfies the descent for quasi-coherent sheaves. So what does it mean? That if I take the union of the images of the spec BI inside spec A, I get the map I cover, so I get a surjection. If and only if I can reconstruct all the quasi-coherent sheaves over A from their restrictions to the open subset. This is similar to what you would do like for vector bundles or for coherent sheaves. Yeah, I mean, the property of being able to restrict to a cover and reconstruct it is precisely, so to a family subset and reconstruct it from the local data is precisely what characterizes the covers. Okay, and okay, this is I mean, in abstract terminology, this kind of property is called descent. Okay, that the property of being able to reconstruct objects of, let's say, modules over A from their restrictions to the category, so to modules, so the base change to all the BIs. And so this topology is defined over the category of affine schemes, and restrict this topology for objects over spec A. So I just consider open embedding and covers over a fixed object. And then this class of maps that a priori would be a class of maps actually is equivalent to a small family of maps, because because I'm restricting the size of maps because I take only finitely represented maps, and the result is a category that is equivalent to a distributive lattice. And via stone duality, I can associate to this distributive lattice a topological space that is a spectral space and is precisely spec A. So this is how you can use abstract machinery, just category theory and algebra, to reconstruct spec A without even mentioning the prime ideals or without fixing it a priori, but just giving a topology on the category of affine schemes. And then that gives you, for any object, a lattice, and that lattice is precisely the lattice of compact open subsets of a spectral space that is spec A. I hope I've summarized this in an understandable way. And now we would like to somehow adapt this strategy to non-commutative rings. And so, yeah, okay, this sentence just says what I already said, so that there is this formal way of reconstructing. Oh, yeah, I use the word frame, that is the language used in the theory of locales. If you know what is the locale, that is like this kind of poset, the distributive lattice you get as the open subsets of topological spaces, and there is a whole theory about that, but yeah, we don't touch that now. But Okay, so there is this procedure of reconstructing the spectrum of space by defining a topology on the Zariski topology, but the knowledge of the Zariski topology of the category of affine schemes. So what we use is just the notion of flat epimorphism of finite presentation, and that makes sense also for non-commutative rings. Why shouldn't we? What happens if we use this notion for rings, not necessarily commutative? And then you immediately go into troubles, because now I want to define a topology. So topology must satisfy the axioms I presented before. So the family of map I'm fixing must be stable by pullbacks. Pullbacks in the category of affine schemes. In this situation, affine non-commutative schemes would be like the opposite category of the category of rings. So pullback would be dual to push-outs in the category of rings. So I need a family of maps that is stable by push-outs in the category of rings. But now the free product is the push-out in the category of rings. And the push-out do not preserve flatness. So we cannot use flat maps, just they don't define a topology. But there is the observation that anyway, by abstract category theory, push-outs always preserve epimorphism. And that's just because they are colimits, and colimits always preserve epimorphism. And we may think to use just epimorphism to define a topology, but that will not be compatible with what happens in classical algebraic geometry. So we would get a topology that doesn't make a lot of sense, and I not really studied, but one could think to consider that, but doesn't seem meaningful. But at least the notion of epimorphism, it's a suitable one for defining topologies. So there are these kind of problems, and since a lot of attempts fail, it means that there should be some new input for having some hope to do some progress in this direction. And so some new ideas must be used, and the idea that I think works, I mean, it's a good attempt, is to use the ideas from derived geometry. So derived geometry, it's kind of a recent development of geometry, and it does providing a lot of new tools and new methods and powerful tools, powerful methods in geometry. And now the subject is quite technical, and I do not have time to really recall what derived geometry is. Here with derived geometry, I always mean derived algebraic geometry. And so I just just want you to use your imagination, your intuition, to just think about derived geometry being what it happens when you replace like commutative rings with simplicial rings or commutative differential algebras and try to do geometry. And here things make sense only up to quasi-isomorphism or up to weak equivalences. And so such a theory as uses some advanced methods of homotopy theory, and the foundations have been developed in the recent years by Lurie and Bambozzi, and nowadays the best language for discussing about these constructions and this theory is the language of infinity category. But today I will not do that. I will mostly rely on giving some informal overview of what's happening. So let's take it for granted that such a theory exists and people wrote down how such a theory works and what are the methods that have been used, that must be used to make sense of all the construction. Then if we accept this, we have that in the derived world, in the world of derived geometry, there are the analogs of all the basic concepts of algebraic geometry. So there is an analog of the Zariski topology, there is an analog of the total topology, the cotangent complex that is the analog of the is the derived version of the scalar differentials and smooth morphisms, etc. And all these notions are usually precise generalizations of the classical counterparts, and sometimes they need some restatement of some of the concept in a language that is more suitable to derived geometry. And this is, for example, what happens for the Zariski topology. That is what we are interested into today. So just discussing the Zariski topology in the homotopical or derived setting, kind of synonymous. So how it is defined, the Zariski topology, in the in derived algebraic geometry? Well, the observation is the following, that if we take a map of commutative rings, now these are commutative rings in degree 0 in this situation, then this map is a Zariski localization. So the localization, I mean the dual map of an open embedding. So what we were discussing before. This corresponds to an open embedding for the Zariski topology, if and only if it satisfies this property, so that the multiplication map is like a derived equivalence between the B derived tensor product over A with itself with B. And also I need to ask that it is of finite presentation. But this property is what, just a second, that I can't see on the screen. Okay. This is the condition that says that the map A to B is an epimorphism in the category, in the homotopy category of simplicial, commutative simplicial rings. So somehow we have simplified the definition of Zariski open embedding by saying that it's just an epimorphism in the homotopical setting. I have to notice that a priori this condition is much weaker than being flat, but it is actually equivalent. And the checking that it is actually equivalent is a theorem, is not an easy property. So, but this somehow it's recalls what I was saying about the non-commutative attempts to define topology, where we could have defined a topology on the category of non-commutative rings by using the notion of epimorphism, but that was not a good notion. But now that we pass in the homotopical setting, the homotopical version of the notion of epimorphism works well for commutative rings. And let's see what happens for non-commutative rings.
Yes.
Yes.
Small question. You use the context of simplicial rings to speak about derived tensor product. But
yeah, in
could
general,
is
you must use simplicial objects
but
or
isn't the well, my question was whether the category of differential graded algebras with the differential pointing downwards is
okay.
not equivalent to that of simplicial rings.
No. Now the
Rationally,
categories
that's true, but
are equivalent.
no, only
No,
rationally.
I mean, yes, you said algebras or yeah, yes, okay. You should use DG algebras only if you are in characteristic 0. You can compare the two. Yeah, and I would use, yes, the simplicial rings, simplicial commutative rings. But actually, I mean, in the non-commutative setting, you can use both. Only the problem is only in the commutative setting. Okay. So, I mean, the monoidal dot-can works for non-commutative algebras, but it doesn't work for.
Yeah, because I recall the paper by Shipley and somebody that proved that.
Yes, exactly. Yes.
Okay, so that works for non-commutative.
Yeah. Otherwise, you are in characteristic 0 and you can do whatever you want. Or I mean, yeah, these are kind of details that when you do the precise computation you may wonder, but
I'm sorry, I have a question. So
yes.
Concerning your crucial observation, what I
Yes.
mean, it is in the language of ring theory means that A and B morphism is a ring epimorphism.
Yes.
And it is true in even for associative ring. Yes. So it is unclear for me that that what is the meaning of finite presentation. And together with that, it is a question, it is on homotopical epimorphism. So let me finish very soon. So what I mean that a grothendieck topology is in some sense, it corresponds to the Gabriel topology of a ring. And on the other side, so the class of ring epimorphism and the localization by Gabriel topology they are not the same. And the nicest case, just as you pointed out, that the case of flat epimorphism. So I mean that what does it mean here that a homotopical epimorphism?
So homotopical epimorphism is just this the meaning of this quasi-isomorphism.
Yeah.
Okay, not finite presentation. So finite presentation is a condition that I will drop immediately from the next slide, because in the commutative and non-commutative setting, it's not compatible. They are not compatible, the two notions. And so what I meant here is that this quasi-isomorphism, I mean, if the multiplication map is quasi-isomorphism, then this is equivalent to say that this map is an epimorphism, the homotopical epimorphism of rings. And I mean, in this crucial observation, I'm just talking about commutative rings in degree 0, discrete commutative rings. And there, what is a finite presentation is clear what it is. And I'm just relating this notion of homotopic epimorphism to the classical notion of Zariski open embedding in this observation. Did I make it clear? Okay.
Yes, thank you.
So, I mean, then from this observation, we can give the definition of homotopical version of Zariski topology, so the topology, the Zariski topology used in derived geometry, in the category of simplicial commutative rings, is defined via finite families of homotopical epimorphisms, so maps that satisfy that isomorphism for which the multiplication map is a quasi-isomorphism, and satisfy derived descent. So the finite families for which I can reconstruct the family of modules from their localization to all the homotopy. And as I mentioned before, we, for now, for the sake of simplicity, forget about the finite presentation of maps, because it doesn't give any problem. It gives a true technical problem. You can use it or not. The fact is that the notion of being finite presentation for a map in the commutative and the non-commutative setting are not compatible. So this will make the discussion a bit more complicated. So I just want to do very easy, straightforward case of the construction. So let's forget about finite presentation. And this is a topology that works for the category of commutative digital algebras or commutative simplicial rings, if you want, and is compatible with the classical Zariski topology of commutative rings when you restrict to object in degree 0. And why this is relevant for non-commutative geometry, what I'm saying is that there is this computation that has been recently done by Chuang and Lazarev, that for a morphism in the category of simplicial rings, now I'm not asking anymore for commutative, so any simplicial ring, the following two conditions are equivalent, that is the canonical map from the free product, the derived free product of B with itself to B is equivalent to the condition that the canonical map, the multiplication map of B from B is seen as an A algebra is an equivalence. And the two conditions look similar, but they have different meaning. And the first condition now is the notion of homotopical epimorphism in the homotopy category of simplicial rings. So now the free product is the coproduct of algebras, and you have that in any category, if the canonical map from the coproduct with itself, I mean, a map is an epimorphism in any category if the canonical map from the coproduct with itself with the map, this canonical map, this is called the co-diagonal map, is an isomorphism. Okay.
Okay. Sorry, is the I mean the derived coproduct is you resolve everything by you take a five-band resolution or cofiband resolution for everything.
Yes.
And then you take the coproduct and that's it, right?
Yeah.
But is it obvious that this is in general that this is a coproduct in the homotopy category? Or is it generally true that the homotopy limit or colimit is an actual limit or colimit in the homotopy category?
Okay, I don't think it's very difficult to prove, but maybe it's not very obvious. I mean, I know an article of this same guy spending some time discussing precisely this point. So I'm sure it is true. I'm sure they spend some time discussing that, so maybe it's not very obvious. But then the other condition, now using the tensor product, that now is loosely related with algebras, because now the tensor product of two algebras is not anymore an algebra in general, because in the non-commutative setting, is a condition about the adjunction between A modules, the category of A modules, and the middle B modules. So this functor should be thought as base change functor between the category of models. Now I will be loose in discussing about right or left models. Now we are in the non-commutative situation. I should be careful about talking about left or right models, but all the construction I'm doing can be worked out for right models or left models, and the result is the same. So I will just say models for left models, let's say. And this condition on this adjunction says that the right adjoint is fully faithful. And so that we can see the category of B models as a full subcategory. A models, so this is a localization of category. And so, but this observation that these homotopic epimorphisms correspond to localization of the category of models can be refined to a more precise statement that I'm about to explain. So now I introduce a bit more of notation. So I denote with loc A the category of the class of all homotopical epimorphisms from a fixed, starting from a fixed object of this. But in general, it may be a class of maps. But there is a theorem now that says that I say many contributors because this theorem has many forms and many authors worked on this topic. So I've not been really able to summarize them here. There is an isomorphism of partially ordered classes between the category of these homotopical epimorphisms and the poset. Now I've wrote poset, yeah, of smashing localizations of the category of models. Smashing localizations are a class of localizations that can be specified. Essentially, they are localizations for which they have the right adjoint is fully faithful, as the one we have seen before. If you ever heard about the Recollament diagram, so they are precisely the localization that give Recollament diagrams. So why this is important is because then, yeah, category of models over A is compactly generated, and then it is known that the class of smashing localizations form a set. So actually we have a poset and not a proper class. And actually here the poset of smashing localization is just by inclusions, because these are all full subcategories of mod A, and I just ordered them by inclusion. Just after giving these notions, I just want to go back to the basic examples to give an orientation of what we are doing. So the basic example is that if we take now a commutative ring, and just we want to add again the notion, the restriction of just taking homotopical epimorphisms of finite presentation, then we get the same distributive lattice we have seen before that determines the spectrum of A. Because of discussion, because of the crucial observation we have mentioned before, and yeah, because of this whole discussion.
Federico, can you repeat what a smashing localization is?
Yeah, smashing localization is these localizations that comes as it's kind of a tautological. I mean, it's a localization where you have the right adjoint is fully faithful, and maybe you need to require some. And I don't remember if you need because we are in a special situation of the category of models, so they are characterized quite with few properties. But
I like the fact that locas are related to smashing ones.
Yeah, yeah. I mean, if you know what is a Recoleman diagram of categories, that's precisely that. All the Recoleman of mod A are are precisely given by a smashing localization.
So are these homologic homotopy epimorphisms always smashing in this mod A setting?
Precisely,
Okay.
they're precisely the same.
Okay, cool.
Yeah, then you can look at the localization or the kernels. Then people talk about smashing subcategories are the kernels of smashing localizations, etc. All of this comes from the work of Niemann of the 90s. That is what is coming now, that if A is a commutative Noetherian ring, then it follows from the work of Niemann that then this poset of all these smashing localizations is precisely equivalent to the poset of the generalization closed subsets of the spectrum of A. Generalization closed subsets are just arbitrary intersection of open subsets of spec A. Okay, I mean, okay, they have a definition that is equivalent to being intersections of arbitrary intersection of open subsets. Okay, so yeah. So from this discussion, we see that it is reasonable to use homotopical epimorphism to try to define a topology on the category of simplicial rings. So the outcome will be compatible with the notion of algebraic geometry, the derived and non-derived. So we have the notion of localization we want to use, so the notion of open embeddings, but what to do for the covers? For the covers, there are still problems, and the problem is that now we have two base change functors, one for algebras that is given with a tensor with a free product, and the modules is given with a tensor product. And so these two functors in the non-commutative case, they are different. Instead, in the commutative case, they are the same functor. And this creates complications and also create the issue of taking the correct definition of a cover. And so, yeah, what I was trying to say that is if I start with a morphism, then I get the adjunction from the category of algebras over A, so that it's just the homotopy category. I mean, simplicial rings.
But is that true? I mean, can't you have simplicial rings whose homotopy, I mean, is not concentrated in degree 0?
Yes.
I mean,
yeah.
Or is that the name that you give?
Yeah, everything can be is in a non-derived situation. So A and B can be non-integer 0. Yes.
So
I mean,
yeah, but what I mean is alg. What is alg?
A notation for not writing these long strings.
Okay, so that's the name of the what you have on the left.
Yeah.
It's not
also mod is simplicial. It's the homotopy category of models. Just I don't want to write the long string, and I'm just abbreviating this homotopy category of simplicial rings below A as algebras over A, but algebras in a homotopical sense. Okay? And also here I have algebras in the homotopical sense over B, and both A and B are simplicial rings. And then, I mean, here there is this adjunction that is given by the free product and forgetful functor. And here, now, the other adjunction between module, the category of modules, is given by the tensor product and forgetful functor. So they are not the same functor. They are not computed in the same way as it happens for commutative means. And so, okay, one consequence of this is that the base change theorem doesn't hold in this situation. I don't want to discuss this issue here. I do not have time. So if you know what is the base change theorem, it's okay. Otherwise, we can discuss in another situation later. But it's a consequence that you can't use some basic theorems that you have in algebraic geometry. So one other consequence of this is that if you try to just use some of the properties that have been used for detecting covers in the commutative situation, that we said that we ask for descent for modules, and this happens when in the adjunction I wrote before, there is, in this adjunction, there is the base change functor is conservative. If we take this kind of class of covers, we don't get a topology. So they are not stable by the free product of algebras. So after thinking about that, you realize that there is a possible solution to this. And the non-commutative Zariski topology is defined using the adjunction for algebras. So the non-commutative Zariski topology on simplicial rings is defined using finite family of homotopy APs. And I ask that the functor from the category of algebras over A to the category of to the product of the category of algebras is conservative. That is similar.
But isn't this also the case in the commutative case?
Yes, this is compatible with the commutative situation. But in the non-commutative situation, this condition is a bit is different, and this is not equivalent. Okay, this does not imply that this adjunction is common. For example, this does not satisfy the same in the non-commutative situation, because the free product.
This is because descent is something about modules, right?
Yes, but in the commutative
so there should be a different kind of descent.
Yes, that's true. That's true. But I think that anyway, it's true that it should satisfy the descent in the commutative situation. But because it's a specific computation, but it doesn't. But that condition implies that the adjunction at the level of modules satisfied the descent, so it's commonality. But it's not the opposite. I mean, if I ask for this to be commonadic, that doesn't imply the condition of a cover. So there are commonadic adjunctions that do not come from covers in this sense. And if I use this condition, I don't get a topology. It's the remark I stated in the previous slide. So one needs to be more careful about what family of common adjunctions on the category models one selects. And my conjecture, I mean, I'm not able to characterize this family of, I mean, we have this family of adjunctions, and they are characterized at the level of algebras, but not at the level of modules. And I would like to say that there is a property of this adjunction at the level of modules that correspond to that of algebras. And my conjecture is that the conservativity at the level of algebras corresponds to faithfulness that is stronger than conservativity at the level of modules. And I can check these on some examples, but I do not know if it's true in general. I tried to prove it in general and it doesn't. I'm not able. So yeah. So that's possible. I mean, that's how the topology looks like. So now just say a few property of what we have obtained, so that and to the related spectrum, because now we have to say that if we fix this topology in the category of algebras of A algebras, then we get a poset and on which we have a topology. I mean, the topology restricts, so we have a poset with a topology. And the theorem says that yes, we have this poset and it should be the dual of this, because then we should pass to scheme and a topology on it. Okay. And this poset is always a lattice, but it's not distributed. So it doesn't correspond to the spectral, a spectral topological space in a naive way, but it is a site, so it is a category. So a poset in particular is a category with a topology, and the site, the category of this site is a poset, and the topology has only finite covers. So there is a theorem that says that in this situation it's always a coherent topos, so it is associated to a spectral topological space. So there is the topos, the site we obtain is equivalent to that of a topological space, and there is a quite explicit formula for describing this spectrum. Now I put this non-commutative spectrum of A, what you get from this construction. So it is a spectral topological space associated to a lattice, in general not distributed, that has a topology, a coherent topology. And
is there a definition of a spectral topological space?
A spectral topological space has several abstract characterization, but it's just equivalent to the spectrum of a commutative ring. So you can characterize them as sober, compact with a base of compact open subsets and D0. And maybe
basically whatever properties that spec of a ring satisfies.
Yeah.
And there's a result which says that any what are these things called? Spectral topological space is the spectrum of a ring.
Yeah, sometimes people like
prime spectrum.
Coherent topological spaces. Yeah, there is an abstract characterization with some topological properties of all the spaces that come precisely from spectra of rings that are the same that appear in stone duality, that like this spectra of prime spectra of distributive lattices. Yeah, also, I mean, since for the results we discussed before, this construction depends only on the category of modules, derived category of modules of A, and so if for derived Murid equivalent links, we get the same spec. So just okay, yes, I have some more minutes. So just some examples of what we get. So if we have a field, we just have a point. Okay, the spectrum doesn't change. For a DDR, also nothing changes. We get the non-commutative spectrum is the same as the spectrum because there are very few homotopological epimorphisms in this case. But then if we already go to Z, we get very big space because we get that the base of compact open subsets of the spectrum is given by this generalization closed subsets of the usual spectrum. So that are like all the intersections of open subset of Z. But, so I mean, it's like the intersections of all the Zariski opens. So you can check that this essentially gives you the Stone-Church compatification of n, where you identify the natural numbers with the prime numbers, so you have countable number of points, plus there is a generic point that lies around. And I want to point out another thing here, that a byproduct of all this discussion is that is not part of what I've been doing, but people that worked on this topic before me well already noticed that there is this problem of localization of rings, non-commutative rings, where if you want to invert some subset of a ring, then this universal object exists, so you can invert object, construct a universal ring that satisfy the correct universal property for inverting these elements. But differently from what happens in the commutative case, the canonical map is not flat and doesn't have the good properties that you would like it to have. And also, I mean, it is similar to the situation we said before, that it's not suitable for defining the topology as it happens in the commutative situation. Like, because this would be some like Zariski open subset would define this kind of construction. But there is another way of inverting elements, and I don't want like now to discuss this here, but it makes sense to homotopically invert the elements, so invert them in the homotopical world. So thinking of R as a discrete object in the category of simplicial rings, and the resulting construction is not always a ring, but is a DGA. And this DGA has the property that the canonical morphism is from R to your localization, homotopical localization is a homotopical epimorphism. So we go back to the situation where homotopical epimorphisms are the class of maps from which you can define a topology, and this is coherent with these localization, classical localization techniques that do not work in the non-commutative setting if you perform them just at level of rings, but if you perform them homotopically, then you get the correct class of maps. So, yeah, I hope I explained this correctly.
Sorry, sorry.
Yeah.
One question. Maybe I wasn't paying attention at the right moment, but for me, you were using simplicial rings all the time, and suddenly a DGA appeared. Maybe the DGAs started some slides back, and I missed that.
Oh, sorry. Simplicial rings and DGA for me is the same thing, because as we mentioned, sorry, let's say simplicial ring, because I mean monoidal Dolka.
Yeah.
Sorry, I just switch back and forth between the things because I'm just thinking up to homotopy. Nothing characteristic zero when you are for non-commutative.
But in any case, your DGAs are homological, right? The differential points downwards, and you do not admit
I usually
non-connected
write them
ones.
horizontally, but
Yeah, but I mean,
I'm used. Okay. All this story can be performed, and probably the best setting is to use unbounded algebras.
okay.
So you can have differential goings in both directions.
Mm-hmm.
Usually, I mean, using homological conventions, I would use the negative indexes.
Okay.
If you use homological conventions, I would use positive.
No, I mean, if what I mean is that if you allow DGAs that are not, that are non-connective, then that's not equivalent to simplicial rings.
No. Yeah, I'd say that I've been quite informal. So okay, this algebra will always be concentrated in degree less or equal to 0 in cohomological will always be equivalent to a simplicial ring. That's true. Although the theory works also with unbounded thing. So was this your question? No?
Sorry, yeah, that well, my question was how did this become a DGA? But it's a simplicial ring.
Yeah, it becomes
it
becomes a DGA, but becomes a
Well,
DGA in the simplicial direction. In the simplicial direction.
Okay, fine.
So maybe connective DGA or something.
Yeah, okay, let's say connective DGA. Yeah. Yeah, it becomes a connective DGA. Yes. Or, yeah, simplicial DGA. And yeah, and there is also from the discussion so far, there is clearly a canonical projection from this new spectrum, this non-commutative spectrum, to the classical spectrum for any commutative ring or EGA. Okay, that is essentially just considering the one of finite presentation. Okay, it's just a sub poset inside this bigger one. Okay, and this gives a canonical projection. Okay.
So may I have a question just
Yes.
for a particular example? So, for example, if we want to get from a ring R and ring epimorphism, which is not flat. For example, we try to invert not only a subset of R, but some matrix over R. So, for example, we take a particular square matrix over a ring R, and we try to invert that. So that is surely not flat. So if we apply a process, what you suggest, so instead of that, we pass to the homotopical or whatever. So then what we would get. So that is the main point when we work with the quiver algebra or whatever. But just to thinking very simply on inverting a matrix. So that is the meaning of the cone localization. When we pass from, we consider a ring epimorphism. That is where the situation do not coincide when you try to consider the grothendieck topology and the epimorphism. So then what the new, as you say, that the new idea of considering homotopical or whatever differentiation graded algebra or thing.
Actually, I haven't worked out these kind of specific examples, so I do not know how to precisely answer to this question. I know a paper where this is discussed. So I don't know, maybe Devashi, your answer to the chat was related to to this?
Yeah, so
something
my
more?
question in a sense was, well, it was related to what An asked. So
Okay,
I was
so
wondering what happens if instead of these homotopy epimorphisms, you consider cone localizations.
I do not know.
Now the ones that you invert a family of maps between projective
Yeah.
modules.
Yeah. I know. And in some situation, you get, I think, some homotopical AP, but sometimes no. I'm not sure. I'm not sure. I know.
Mhm.
I know that people really studied this, but it was not something I was
Okay.
interested into.
Yeah, I think it's not
so-
automatic. I think it's not automatic.
Right. I mean, okay. So then, on a related note, so do you have examples of homotopy epimorphisms which show up in like non-commutative geometry? I mean, I know that these homotopy epimorphisms are localizations in algebraic geometry.
Yeah,
Do you
the
have,
next
or
slide
in analytic
are
geometry as well?
a couple of
Okay.
examples of non-commutative rings. Yeah.
Okay.
Yeah. So yeah, I mean, only simple examples are known and are classified. So, for example, we can take path algebras of quivers, finite quivers, like A2, and then you can compute that the spectrum is just discrete topological space in 3 points, because I mean, then you have that the category of modules, as always, derived category, as 3 smashing localizations that correspond to the indecomposable representations of A2. And then here it's a situation where you can check that the covers really correspond to the faithful family of localizations of the of this category, and then work out the. I mean, you get this lattice that is not distributed because you have one top and 3 elements. Yeah.
So to you, AN has N edges and N+1 vertices. Because I was wondering the 3. The 3 must be that there are 3 vertices in your
yes.
in your quiver, right?
Yes,
Okay.
these are 2 vertices and 1 map. Yeah. Okay. And yeah, and the lattice of smashing localization is non-distributed in this situation, but still you can work out. You get lattice with a topology, and you see that the resulting associated topological space is discrete. Okay? And the conjecture is that for all path algebras that have finitely many indecomposable, for a quiver that have finitely many indecomposable representations, you always get discrete space on those indecomposable representation. And but I haven't checked in generality. The other example that I know that is essentially worked out is the Kronecker algebra. So that's the path algebra of this quiver, and we know that it is equivalent. I mean, the category of modules over A is equivalent to the quasi-Fourier shifts over P1, and then the smashing localizations of this category have been classified, and they correspond to the twisting shifts, and then all the generalization closed subsets of P1. So we have this kind, just again, a non-distributive lattice. I haven't, probably I should have done some graphs for this. It would have helped a lot. But the way they are distributed is that there is a countable family of localizations that are like disjoint from all the other ones, and then there is another piece that is P1, and the topology that puts together all these points is a cofinite topology. So Like an open subset is everything but finitely many of these components. Okay, so we can describe this space in this situation. I think okay. Here it's okay for the construction of the spectrum. I can stop here. Essentially, I have another slide saying that if you want to upgrade this to some more structural space, like putting a structure shift on this thing, things get complicated. So it doesn't really work immediately, and there is a work to do. But since I'm over time, I just skip this, and maybe if you have questions, I can say more about that. So thank you.
Okay, thank you very much for your talk, and sorry for the many interruptions, but they reflect our interest in your talk. Are there any further questions from the audience before I stop the recording?
Yes, I have a question.
Mhm.
Sure. Sorry.
Please.
Can I? Yes.
Yeah, please ask.
My main point is always in that. So when you get somehow by localization, by whatever, even we get a flat epimorphism, then everything is nice. So, and as I see that to overcome the problem when a localization, just like the cone localization on a proper square matrix, so not on row matrix or on column matrix, then you suggest a new tool by considering a homotopican thing. And what is the plus when we can get in that situation?
Yeah, it's a kind of a generic question in the sense that depends what your goal is. What I can tell you is that these notions can be organized in a way that they form a topological space, and you can do some geometry. And then I don't know. It depends to you on how you want to use them. I would say. What I can tell you is that for example, I skipped this, but I would like to get some Gelfand duality, and what you get is that there is a local to global principle in the sense that you, as we mentioned, the condition I put on covers gives descent for modules. So I can take a module and reconstruct it via the monad I get from the category of modules and its localizations, constructing something that is called this Amistur complex.
So yes,
does not. Yeah.
In the Amistur complex, you use n-fold tensor products, right? Tensor
Yes,
products.
but this is the Amistur complex of yes, it would be yes. This yeah, in this case, yes, it is of the tensor product. Yes, it would be the Amistur complex of a comonad, I would think, but this comonad, yes, is given by the tensor product, but it doesn't correspond with the free product. That is the one that gives the correct intersections, topological intersection of the localizations. But that can't be used to reconstruct things. We said it doesn't give you descent. So there is some certs. So the notion of shift doesn't work somehow, but still you can localize and from local data reconstruct your global object. But with the formulas that are different from the one you would get by computing check cohomology. That's the meaning of this last slide. So coming back to the question is that what you can do, I mean, if you are studying some problem, some algebraic problem on A, you can try to localize it, and then you have some formulas to go back, solve it locally and go back to the global question and try to use this global, local to global way of reconstructing objects. But the formulas and the mathematics that is behind this is not that of topological, I mean, ring space or shift on a topological space in the usual setting. It must be modified. And the theory for doing that is still a work in progress. So in this part of the story still has not been properly worked out. So this last slide is about what we are doing now, and we hope that then will lead to some proof of Gerfan duality in the non-commutative situation. Yeah. Hope it gives some clue.
Yes, but exactly that is the problem, that when we try to localize, then the localized result was so complicated that we are not able to understand the localization. So that is why we need a new idea, as you mentioned at the beginning, that passing to some better, I don't know what you say, homotopical or modulo the homotopy, we would get a situation where we can control everything.
Yes, that's true. But I think in actual computations, the computation I'm describing in abstract will be quite difficult to perform, but everything is as is formula, and theoretically it's possible to write down what you want. Then I don't know. I mean, I do not have any explicit example of I've solved this problem, this computation using this method yet, but at least there are some receipts for things that you can try to compute.
Okay, I suggest we stop the recording now. You can still discuss afterwards.